this video, I am going to quickly show you how you can easily run exploratory factor analysis in JAMOVI. I am going to also tell you what are the important steps and what are the important considerations while performing exploratory factor analysis. For example, choosing the rotation method, whether we should go in for oblique rotation or we should go in for orthogonal rotation. Along with this, I am going to tell you the significance of assessing KMO and measure of sampling adequacy MSA as well. We are going to generate the weighted factor scores in case we want to conduct a regression analysis further or conduct a ANOVA further. We can do it through the factor scores generated through EFA. So let us start and dive into the world of exploratory factor analysis easily with JAMOVI software. Here we are in our software. I have loaded the data. You can check over here. We have 305 respondents in this data. So the case ID goes up to 305. And then we have occupation, wherein we have three categories of occupation. We have gender, 0 denotes female and 1 denotes male. Though we are not going to consider these variables as they are categorical in nature, in exploratory factor analysis, we always consider the continuous variables in our data set for doing EFA, immaterial of whether they are independent variables or they are dependent variables, and they should be directly observed independent variables and observed dependent variables. So in this case we have food quality, which is marked upon Likert 5-point scale, and we are having 4 items of food quality. So generally speaking, we don't assign these indicators a particular association with a latent variable before doing exploratory factor analysis. So there will be a list of items in your questionnaire, and now you want to explore that which items come together to explain a particular latent variable, so that you can make up that factor or make up that latent variable, gather its score and do further regression analysis. This is usually done when you don't have a strong theoretical background of ascertaining that certain indicators form a latent variable, and you are abruptly putting some of the indicators in your data, some of the statements in your survey questionnaire to be answered by the respondents, and later you want to group those variables together, group those indicators together, which meaningfully explain the latent variable. So that is the fundamental aspect behind doing exploratory factor analysis. In case you are certain about the indicators or the latent variables which have been tried and tested before by previous researchers, then there is no need to conduct exploratory factor analysis, as EFA is a scale development procedure. So basically it's a scale development procedure, and it does not distinguish between independent and dependent variables. So coming back to our data, food quality with 4 indicators marked on Likert 5-point scale, service quality on Likert 5-point scale, again we have 4 items over here, ambience 4 items, and price fairness 4 items, and customer satisfaction, which is deemed to be our dependent variable, is again having 4 items marked on Likert 5-point scale. Now sometimes you'll feel that Likert items are ordinal in nature. Why we are doing EFA with them? So there has been a great amount of debate upon treating Likert items in a questionnaire, how you should do the data analysis for these Likert items, because the interval difference between each Likert point marked on a Likert scale may not be equal for everyone, right? But we assume that there's an equal difference between 1 to 2, 2 to 3, 3 to 4, 4 to 5, in case it's a Likert 5-point scale. So when we assume there's an equal difference, in that case we say that it is an interval scale. An interval scale happens to be a part of continuous data category, right? It is a part of continuous data category. So that's why we consider them as continuous. Now, once you click over here, I'm going to show you some features of JAMOVI, how you can change the scale. So say service quality, I double click it here and we see measure type is ordinal in this case, because since it's a Likert item. So we can keep it ordinal or we can change it to continuous as well. This will not affect the results in JAMOVI. But to be sure, because we are going to generate the factor scores, the weighted factor scores of each of the factor being generated, so it's better to keep it continuous in nature over here. So how we can change it for all of them together? Let me show you. So starting from food quality till the last indicator of customer satisfaction CS4, I want to make them all continuous. So all of them are selected and I click on continuous. So now you see they all have become continuous in nature, right? Now I'm going to start with exploratory factor analysis. For that, I need to go to analysis and then I go to factor. So here is the factor and I go to exploratory factor analysis like this. Now I'll put all the variables, all the continuous variables you see here. We select all of them. I press the shift button and scroll it down up to CS4. So I include them over here, you see. So I got this list of 20 indicators and immediately you see the EFA results have been produced. So they have been bifurcated into 5 factors as we supposed our data has 5 factors. One is food quality, service quality, ambience, price fairness and customer satisfaction. So they have been allocated their factors by EFA. Now, what settings we need to do over here and what we need to check here. So first is extraction method should be minimum residuals. So we go with minimum residuals. That's a prescribed method. Rotation is oblimin mentioned over here. So oblimin rotation allows the underlying factors to correlate with each other. Since we are doing a study in social sciences, we are studying people behavior. So when we are talking about the correlation between the latent variables, then if we want to allow the correlation while factoring happens in EFA, we should go in for oblique rotation and the type selected over here is oblimin. In case we deem or we assume that there is no correlation is completely missing in the different latent variables in the different factors of our study, then we should go in for orthogonal rotation and the best and widely used is Varimax. Since we are assuming that our data has correlation and it's a social science perspective study, so we go with oblimin, that's the prescribed one. Now we need results for Bartlett's test of sphericity and we also need KMO, Kaiser-Meyer Olkin measure of sampling adequacy. So we take both of them. Now, KMO tells us the proportion of variance among the variables that might be common. So in EFA, when you have a KMO value, let us see the KMO value. You have this MSA value generated for KMO, that is measure of sampling adequacy, at least 0.50 value should be there because the items below 0.50 should be dropped. So see here, we have all the MSA values which are above 0.50 in this case. So no item should be dropped in this case. And KMO value basically tells us that whether our items are acceptable, they are good, and they should be at least 0.60. So we say that at least 0.60 we are having in this data. That means the items are quite acceptable and they are producing meaningful factors. They would be producing meaningful factors. There's no indicator or no item which does not solve our purpose. Then we check the Bartlett test of sphericity. So the p-value should be significant. So in this case, you see it is less than 0.05. So the value is significant. It tests that items share enough correlation to be grouped together into factors. So items share enough correlation to be grouped together into factors. That is what is being told to us by this p-value, which is significant. So if the p-value is greater than 0.05, EFA cannot be performed. So it cannot be performed as items would not come together to form a factor, right? Then we check the minimum residuals. We talked about minimum residuals. Let me tell you one more thing about minimal residuals. Now, minimum residuals works well even if the data slightly violates the multivariate normality. So this is the prescribed method. Since we are not having perfect normality in our data, so we go with minimum residuals extraction method, which works well even if the data slightly violates the multivariate normality, right? And it is the default setting for EFA in JAMOVI. When we go with parallel analysis for extracting the number of factors, we got 5 factors individually, distinct 5 factors. And in this case, we can go in for eigenvalue as well. But why eigenvalue based on eigenvalue is not preferred? So let us talk a little bit about this. Actually, parallel analysis seems to be better than going with eigenvalues analysis criteria, because that Kaiser criterion simply retains every factor which has an eigenvalue greater than 1. So parallel analysis asks a more meaningful question here, that is the factor explaining more variance than that would be expected purely by chance? So it simulates the data. It does this by generating many random data sets with the same sample size and number of variables as your actual data. And it then compares your observed eigenvalues with the eigenvalues generated from these random data sets, as we can see in this scree plot. So you see here, this is the simulation data depicted by orange dots, and this is the actual sample data. So the number of data points which are lying above this simulated line, these are the number of factors being extracted through parallel analysis. So in this case, we see 1, 2, 3, 4, 5. So a factor is retained only if the observed eigenvalue is greater than the random eigenvalue rather than the eigenvalue which is fixed to be 1. This greatly reduces the chance of retaining factors that arise from sampling error. And Kaiser criterion becomes less reliable in this case because it may retain too many factors, that is, it can lead to over extraction, or it may retain too few factors, that is, under extraction. Its performance depends on the number of variables, communalities, and sample size. So, in case of eigen value criteria, that is Kaiser criteria, several factors to be looked in for. But parallel analysis is something which gives us a more robust and reliable estimate of the factors being extracted from our data set. So it's recommended that you go with parallel analysis, which is not readily available in SPSS, but you can go and install an extension in SPSS. Many methodological texts and software packages recommend parallel analysis as the preferred factor retention method. So in this case, we see that it goes well with our theoretical assumption of having 4 independent variables and 1 dependent variable. So it aligns well with that theoretical assumption as well, and it is well able to give us 5 factors which load well, whose indicators load well on the factors. So we go with this solution of parallel analysis. Let us check on factor summary and the information we get from this. So you see here this factor summary table, sum of square loadings, which is comparable to the eigenvalues. Since they are all greater than 1, we can say that each factor explains more variance than explained by a single item forming that variable. Similar interpretation as we do for eigenvalues. Then we look at percentage of variance. So we see here that all have a similar percentage of variance. That means each factor is explaining us amount of variance in the indicators through which it is formed, and this amount of variance is probably equal for all of the 5 latent factors which has been extracted in this data. So that means none of them is dominating the other, right? They are all equal in their variance, equal in explaining the variance of the indicators through which they are formed, right? When we look at cumulative percentage, we get to know that all 5 factors come together to explain 64% of the variance. So we can say the 5 factor solution explains 64% of the variance in all the observed indicators which are there in our data. So based upon eigenvalue, if I check the same thing, I'll get 4 factors you see over here. So based upon eigenvalues greater than 1, that means that each factor is able to explain the minimum amount of variance which is explained by each single item forming that latent variable. So at least that much amount of variance should be able to be explained by a latent variable, which is explained by any one of the indicators, at least that much. So that's why we say eigenvalues greater than 1. So if we go by eigenvalues greater than 1, we see we have a 4-factor solution over here, wherein we see service quality, 4 dimensions, 4 items of service quality, and 4 items of ambience gel together to form a factor, as shown to us by the scree plot also. So in this scree plot, this dotted line depicts the eigenvalue of 1, and the blue points lying above that line depicts the number of factors 1, 2, 3, and 4. So we are going to base the number of factors upon the eigenvalues. So based upon the eigenvalues which is greater than 1. Why do we take it to be 1? We take the eigenvalue should be greater than 1 to filter out the weak factors prevalent in our data. So if you square all factor loadings of a specific factor across your variables and then add them, you get the eigenvalue, right? And the eigenvalue of, say, for an instance, 1.49 means the factor explains equivalent variance of 1.49 individual standard variables. This means the factor holds more information than any single item, that is a questionnaire item. So that is why we're looking for this eigenvalue. And as per this Kaiser criterion, the Kaiser-Gottman rule of 1960, the factor retention should be done based upon eigenvalues which are greater than 1. In case it is lesser than 1, then this means the factor does not hold more information than any of the single item or single questionnaire, because we are looking at a factor being formed by indicators, and especially this is being done for reflective items, right? Not for formative items. We don't do formative items exploratory factor analysis because they lack in correlation amongst them, right? So now we see factor loading. So hide loadings below 0.5. So we can say that below zero point 0.5 you should hide the factor loadings, and then we can say sort loadings by size, and additional output we can check the scree plot, we can check the factor correlations, because again factor correlations will help us to determine the type of rotation. As I told you, if the inter-factor correlation is greater than 0.35, then you go in for oblimin. Otherwise, if it is lesser than 0.20, you go in for varimax, that is a type of orthogonal rotation. So that is the way we can use it. Simply we can check on the factor correlations and then decide upon the rotation method. Then we come to the important part, that is save factor scores. So we want to save the factor scores for further conducting regression analysis or analysis of variance, that is ANOVA analysis. So for that purpose we can save the factor scores, which are of course better than manually doing the composite scores arithmetic mean in Excel, because arithmetic mean assumes that each of the indicator carries equal weight in explaining the latent variable. Now in this case, when we take the weighted factor scores, the system does not assume that each item carries equal weight to explain the underlying latent variable, and that is why it is important to extract the weighted factor scores which are generated through the software. Now one of the most widely used method over here is Thurston method, which you can rely upon. So we go with Thurston, which is the default in JAMOVI. Now you see here inter-factor correlations, what we just spoke about. So what is the correlation between factor 1 and factor 2? It's 0.440. Between factor 2 and factor 3.449. So as I told you, it is greater than 0.35. We can go in for rotation method, that is oblimin rotation, right? Which assumes that there is correlation between the factors, and we can see here this correlation, though here we can see this less amount of correlation. But if this correlation had been less than 0.20, then in that case we would go in for varimax. Even the scree plot tells us that how many factors can be extracted. So you see above the value of 1, as we placed eigenvalue 1 over here, the threshold was 1. So this is 1. This dotted line depicts 1. So in this case, you see that how many factors do lie upon this dotted line, above this dotted line. So 1, 2, 3, 4. 1, 2, 3, 4, right? So there can be 4 factors which can be extracted. So that is how you interpret the results, and the preferred is based upon parallel analysis. There would be 5 factor scores in our data sheet. So let us check whether they have been saved. So I go back to the data sheet and you see here factor score 1, 2, 3, 4 and 5 have been saved. 1, 2, 3, 4, 5. So I can use these 5 factor scores later on to conduct regression or ANOVA analysis. I hope the video was informative and useful for you, and it's quite easy and convenient to conduct EFA in JAMOVI rather than going in for SPSS. Still, SPSS, some people would like to use SPSS, but if you don't have the access to SPSS, you can use the freely available JAMOVI software.